We're going to look at a few rules which will help us do our calculus a bit quicker, a bit more efficient. First one goes by the name of the chain rule. It's also called implicit differentiation. It's also what we use in this thing called rates of change. All the same thing, the same basic idea, which is this. However, I never use that, but that's formally what the chain rule is. It's much easier like that. If you remember it like this, then basically you say it in your head as you do it, and this is what you do. It's bring down the power, lower the power, diff the inside. Anarchy, if you like. Think of it like anarchy. So you're bringing down the power. Right? You bring down the power, and then lower the power. So once you bring them down, you chuck them on the ground, you see. Lower the power. And diff the inside. Well, basically, once you've got them on the ground, you want to get everything out of their guts. Go out and everything. You diff the inside. So anarchy. Let's demonstrate. Here's the one we looked at yesterday. It was a very simple one. I probably wouldn't use this idea for this one, but I'm just using it to demonstrate how it works, because of course that's not hard to expand out. So bring down the power, lower the power, which is essentially the same as what we were doing for polynomials anyway. It has this added bit of diff the inside. So bring down the power, 2, lower the power, 1, but now we diff the inside. Whatever's in those parentheses I'm going to differentiate, which in this case is just 2. And we get our answer, and that is of course the same answer we got yesterday, albeit factorised, and yesterday it wasn't factorised. That now gives us the advantage of we don't have to expand this out. I mean, that would take us a bit of time to expand the whole thing out. So we just bring down the power, 7, lower the power, 6, diff the inside, derivative of 3x minus 4 is 3. And that becomes 21 3x minus 4 to the power of 6. Same idea again. Bring down the power, 3, lower the power, 2, diff the inside. Well, if I differentiate the inside, x squared minus 2, I get 2x. 6x, x squared minus 10 squared. Bring down the power, but there's a 5 out the front, so 6 5s become 30. Lower the power, 5. Diff the inside. Well, differentiate 4 minus 2x, I get negative 2. Negative 64 minus 2x to the power of 5. It's this idea, as I say. There's another way of writing it, and I prefer to write it like this, because then it can be applied to these things like implicit differentiation and rates of change. The idea basically is, well, dy dx, what we're really doing is we're differentiating it with respect to t and then multiplying that by to t dx. That's effectively what we're doing. It's similar to what I showed you yesterday in the setting out. It's that idea is what we're doing. But now if I think of it like that, I can differentiate things in parametric form. See, I don't have to recombine these and find the Cartesian equation, because I'll just differentiate each bit with respect to t. To differentiate x equals 4t, we get dx to t is 4. Differentiate y equals 2t squared, I get dy to t is 4t. But I want to find dy dx. Because I want dy dx, that's dy to t times the t dx. For mine it'll be 4t times a quarter, the 4's will cancel, and it's just t. So I have the derivative, but in terms of the parameter rather than in terms of x or y. If I wanted it in terms of x, similar to what we saw with parametrics, all I got to do is eliminate the parameter. X is 4t, so I know t is x on 4, so that would be the derivative, x on 4. I could always do it that way. So that is our wonderful chain rule, also known as anarchy.